All right, once again, jump into the second example for equilibrium. So if you haven't done the first example on your own, go ahead and do that. In this example, we have 0.5 molarity sample of NaOCl placed in a reactor and kept at a constant temperature until the system reached equilibrium. The contents of the reactor were then analyzed and found to contain 0.028 molarity of chloride. Calculate K at this temperature given the following balanced chemical equation shown here. Okay, so we know we're looking for K, so let's go ahead and write our expression for K, because we know that's where we're headed. So K is going to be equal to products raised to their stoichiometric coefficients divided by reactants raised to their stoichiometric coefficients. So in this case, that means we have NO and Cl2. Stoichiometric coefficient for chloride is 1, so this is just raised to the power of 1, and we don't need to do anything. For NO, our coefficient is 2, which means we need to square this term. And the same thing for our reactant NaOCl. Okay, so we are given the concentration of chloride at equilibrium, which means we know this guy. We're looking for K, and we know how much NaOCl we put in, but we don't actually know how much there is at equilibrium. So that means both NO and NaOCl are unknowns. So we have one equation with 3 unknowns, which seems like a lost cause. But alas, it is not. So what we have to do is go back to our governing equation, or chemical equation, and think about what these stoichiometric coefficients mean. Okay, so this next part, I remember having a hard time digesting this fully when I was learning this. So I'm going to draw a little picture and go a little slower. Sorry if it's obvious to the rest of you, but hopefully this will be helpful. Okay, so let's say I just start with 2 molecules of NaOCl. Okay. Now these are going to react, transform, and I'm going to have some number of NO molecules and some number of Cl2 molecules, right? Okay, but if we look here, I've got an NO here and an NO here. So that means in order to have a balanced number of atoms on each side, I need to have 2 NOs on this side. Okay? So NO, 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 NO. Now when it comes to Cl, chlorine, I've got a chlorine here and a chlorine here, and 2 chlorines and chloride. So that means this is already balanced. Okay? So I've got 1 chlorine, so 2 chlorines on this side, 2 on this side, and I'm good. So what that means is, if I put in 2 molecules, let me put that where you can see it. Ooh. If I start with 2 molecules of NaOCl, I'm going to get 2 molecules of NO and 1 molecule of Cl2. Okay, so remember we're keeping track of the individual elements, the number of atoms of the individual elements, not of the species, okay? All right, now what if instead of starting with 2, I started with 4? So NaOCl, 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 NaOCl. It gets a little worse each time. Okay, so these are going to form some number of NOs and some number of Cl2s. All right, and just like last time, 1, 2, 3, 4 NOs on the left-hand side means I have to have 4 NOs on the right-hand side. Okay. Now, if we look at Cl's, I've got 1, 2, 3, 4 Cl's over here, 2 in each chloride, so that means I have to have 2 chlorides. All right. So what that means is, when I start with 4 NaOCl, I get 4 NO and 2 chlorine. And if you remember previously, we had 2, 2, and 1. All right, so if we kind of extrapolate this pattern, what's going to happen is for however many NaOCl is consumed, we're going to form the exact same number of NO. Okay, so if I consume 4 NOCLs, I'm going to produce 4 NOs. If I consume 2, I'm going to produce 2. But the flip side of that is how do I want to say this? Basically, the number of NOCl is going to be equal to the number of NO. Number of NOCl consumed is equal to the number of NO formed. And both of those numbers are going to be exactly twice as much as the amount of Cl2 formed. Okay, so if we wanted to write that in a sentence, we're always going to have NO formed is equal to 2 times the amount of Cl2 formed. And we also know that NO formed is going to be exactly equal to the amount of NOCl consumed. Okay, so we actually have a pretty straightforward relationship between all these concentrations. Now we just need to do some organization to help us solve this problem. And what I personally find easiest is to make a little table. So we're going to start with initial concentrations, and then we're going to have change in concentrations, and then we're going to have final concentrations. And we're going to do this for NOCl, NO, not quite, and Cl2. Okay. All right, so let's start with what we know. We know that we initially add 0.5 moles of NOCl. That's given to us in the problem. And we know that at equilibrium, we have 0.028 moles of Cl2. Okay, so that means, or well, actually, we also know that we initially start with no NO and no Cl2. Okay, and then again, this is what we're trying to get to in order to solve this problem. Okay, so let's fill in this table. If I go from initially 0 chloride to 0.028, then I know I have a change of plus 0.028. Okay, and I know that if I form 0.028 moles of Cl2, then I have to form exactly twice as much of that as NO. Okay, we can also see that directly in the stoichiometric coefficients. This has a coefficient of 1, these both have a coefficient of 2. Okay, so basically what that means is this value right here is going to be twice as large as this value. So multiply 0.028 by 2 and you get 0.056. Okay, which means we know this number now. 0 plus 0.056 is equal to 0.056. So now we've got 2 of our final variables that we need. Okay, now let's look at the change of our reactant, NOCl. We know that the amount of NO formed is equal to the amount of NOCl consumed. So if I add 0.056 NO, I have to subtract 0.056 of NOCl, which means this final value is just 0.5 minus 0.056, so we get 0.444. Okay, so now we have everything we need. All right, and just keep in mind that these relationships up here are all about the change in concentrations, not about the final concentrations. So for example, if I were to have started with something non-zero in Cl2, like maybe I had 1 mole as a hypothetical, I would still add 0.028. Well, actually, let's not do that. But basically what I'm trying to say is that these relationships only deal with this middle row, the change, okay? A common mistake people make is putting all these numbers in as the final values. But as we can see right here, that would give you something very incorrect. All right, and now all we have to do is just plug these numbers in to our equation for k. And if you do that, you get a k equal to, let's erase some stuff here. So plugging all these values into this expression, you should get a value of 4.5 times 10 to the minus 4 molarities for your final answer. All right, so make sure you're familiar with this process in this table. It comes up a lot in chemical transformations, so make sure you have this down.